Hello everyone, I welcome you all to this the 13th day of MATLAB Simulink Masterclass series. This is Malapan from Pantech Solutions, and today our topic is DC motor speed control in MATLAB Simulink. So in this topic we are going to cover about what are all the types of the motors, what is the working principle, and how we can control the speed, and what are all the applications, what are all the types of machines are available in the market, and we will see about some demonstrations how to control the speed in the MATLAB Simulink. So by that way we can vary the suppose if we vary the speed, then we can equally generate a control algorithm for for the target application based. And if you take a DC motor, so in this motor in market variety range of motors are available. So if you take a small DC motor, this is for toy controlled applications. So like for any kids toys, this you can find this kind of motors. Again, smaller DC motors are also available, and vibration motor for vibrating purpose in your mobile devices. There is a vibration motor is there. So for again that motor will be very smaller than this motors actually. And similarly for higher range of, again for a tie control application itself, higher range of motors. Similarly this is for industrial automations motor, so it's similar, looks like a PMDC machines. And again if the power ratings goes above 500 wattage, then this kind of motor will be available in the market. And for 5 HP machines, so in this motor, that mounting structures and shaft and coupling mechanism and everything will be available in the yoke itself. And similarly for 10 HP machines, some for a huge industrial applications, so higher range of motors will be used. And let us take a working principle of this motor. So in this motor major parts are 5 numbers called magnetic stator magnets and rotor coils and commutator along with the shaft and brushes. So if you apply the voltage to the machine, so it's that voltage will be converted by the use of brushes. When the alternating voltage will be applied inside the motor, then based on the opposite fluxes with respect to the magnetic poles, the force has been generated inside over the shaft. So if the force generated, then the motor will starts to rotate. So by this way we can understand the motor working principle. Again, this is very basic theories, and you can get it in your textbook itself. And if you take about types of the machines, in this basic, I am in electrical machine, it's a variety of types are available, but particularly if you take a DC motor, so there are again 4 major classifications are there. One is called a DC series, shunt and compound, and PMDC motors. Again, in the low range applications, PMDC motors are used widely in this industrial purpose. And if you take about speed control logic, see actually how the motor speed can be controlled. So by logically, if you can say, like we can classify it again 3 types. One is called the flex control method, and another one is called the armature and rheostat control method, and the third one is a voltage control method. See actually here the input to the machine, input voltage to the machine will be constant in the flex control and armature rheostat control method. Then inside the in addition to by using the rheostat, we can adjust the speed of the machine. So by in that way again it's has a unique features, advantages and disadvantages. These are just basic theories. You please check in your textbook. And similarly again that important concept called voltage control method. Again in this voltage control method, two methods are available. Basically we can say it's a multiple voltage control method, and the second one is that word learned method. So that is the word learned method is the again proof of concept, not actually widely it's not used in the industrial purpose. But voltage control method widely used again this has a variety of advantages and unique features. We can control the machine at any range. So in that aspect, again this motor is used. So we will see one case study how this motor actually controlled in the industry. We will see in the next slides. And for understanding the speed control, we have a power converter called Hutch bridge converter. So in the Hutch bridge converter, you can get four terminals. One is called the positive and negative, and another one is that terminal A and terminal B. And it has four switches. So switches nothing but solid state switch called MOSFETs or IGBT or SiC devices or GaN devices. So any devices you can use it based on your applications, like a current and voltage. You can choose whatever you want. And this MOSFETs, by applying the PWM, we can control these MOSFETs. If you control the MOSFETs, then we can control the speed of the machines. Similarly, we can do whatever we want with this PWM. And if you take a motor, again there are two terminal. One is a A and another one is a B. For DC machine, we can call it as a terminal. So here again the positive negative will be there. If you reverse the voltage, then reverse the voltage to the motor, then nothing will not be issue. The motor rotation will be reversed if you apply the reverse voltage. See, for example, if A is a positive and B is a negative, then if you are applying at negative voltage at the A point and the positive voltage at the B point, so the motor will start to change its directions, right? So let us see how this motor will be worked by logically we can say, right? We can discuss. See, if you apply the PWM to this switch 1 and switch 4, so this positive voltage, see here this positive voltage will flow via switch 1 a motor and switch 4, and then it's returned to the ground, right? So in that condition, if you adjust the pulse width, see here the pulses for lower pulse width, the motor speed will be very low. For the higher pulse width, the motor speed will be high. So by changing this pulse width, we can adjust the motor speed. And similarly, if you take a reverse, if you turn on switch 1 and switch 4, so in that conditions, the positive voltage will be applied via S2 and motor and S3 and return to the ground. So here the negative voltage is applied. So here for the terminal A got a ground pin and terminal B got a positive voltage. So in that condition, the rotation of the motor will be in the reverse mode, right? So similarly, by this method, by changing this PWM method, we can control the speed. But here again, few more points are there called braking. See here, if this motor is going to use in that automobile applications, the braking behavior is an important behavior. So how we can brake the machine, or how we can stop the machine from the starting position, from the starting condition to standstill conditions, how we can achieve it, how we can start the machines. The start the machine nothing but initially if you apply the entire voltages, definitely that voltage will give that voltage will disturb the entire magnetic system inside the machine. So in that conditions, the transient period may happen. So if the transient period occurs in that period, during that transient time, the current, torque and mass speed of the entire machine will have a transient behaviors. So during that transient period, that all the parameters of the motor will not be a steady state. So it will change change the behavior parameter on time basis. So in that to avoid the huge fluctuations during the transient period, people will use a soft starter method. So in that aspect, that starters came into that picture. And similarly, if you if you want to develop an entire speed control for your target applications, so we have to follow certain procedures. See, let us take this entire block diagram. So this is a motor for controlling the speed control of the to control the speed. We need a one microcontroller. So that microcontroller may be 8-bit, 16-bit, 32-bit, whatever you want. But basically it needs a ADC, PWM and DAC. That is a digital to analog converter. So this three, in addition to that, communication channel. So these four peripherals are important peripherals. So we should choose the peripheral based on your motor load. And the other thing, again, the sensing components. The sensing components nothing but, so we have to sense the motor speed. In addition to that, current or voltage. So if you're talking about vector control, then where we need in that conditions we need to sense current, voltage, everything we should sense. So, but for some applications, motor speed itself enough to regulate the speed of the machine. So like that, based on our target applications, requirements, we have to choose the sensing elements. So again, in our agenda, we have a sensing sensor design topic about actually here, the day 19th AC DC current, voltage and measurement sensors list there. So here we will discuss how the DC voltage can be measured, AC voltage can be measured, and how we can sense the speed of the machine, and what are all the methods or what are all the sensors are available in the market. So everything we will discuss in this topic. Keep engaged with the entire 30-day session. You will definitely it will help you. And next thing, okay, you have controlled the motor, you have developed the algorithm, and you have sensed everything, and then you have perfectly developed the control algorithm. But you have to interface, or you have to take a data to the outside world, right? So for that one, you need a GUI, that is a graphical user interface setup. So in this graphical user interface setup, that basic communication channel is called UART, Ethernet, USB. Again, some of additional protocols also available called CAN, LIN. So for vehicle automobile applications, we have to use some of different applications, different protocols. In industrial applications, again we have additional Ethernet, RS485, so the Modbus, this kind of additional protocols. See, actually in that protocol also again there based on your requirement, you have to choose the protocol facility. And for sensing the speed, we have a variety of sensors called tacho generator, magnetic pickup, optical disc, along with sensors, and Hall effect sensors, rotary encoders. And similarly, for power devices, you can get a transistor, MOSFETs, IGBT, GTO, thyristor. Again, SIG devices, GAN devices. So we can choose whatever we want. And similarly, we have to use any one of the process controller called microprocessor, microcontroller, ARM processor, and DSP processor, and FPGA also we can use. Again, if the system requires, say for example, I am going to run the machine in the open loop, then we don't require anything like ARM or FPGA or DSP, whatever we want. Just Arduino controller is enough to run our machine. So again, we have a demo in our schedule with how we can control the speed of the induction motor using Arduino by simple logic. We will discuss in our topic. So again, and let's go to the top demonstration. So in this demonstration, let us go for MATLAB. Open the MATLAB. Take a DC machine. So here the DC machine is available in this block. DC machine. In this DC machine, we can use all the kind of DC machines called the series, shunt, and COM board, whatever we want, we can connect it. So now we are going to use separately excited DC machine. In this machine, just take any rating called actually 5 HP to 240 voltage, 1750 RPM, and 300 voltage. So here we are going to take this as a for our examples. And for this we need two DC voltage levels. So take a DC voltage source. For one is for armature, and second one is for field. First we will verify basic DC machines whether it is running or not. Then we can go for the controller. So now we are going to run the machine. Take a bus selector to get to measure the machine parameters. See, and for this we need a power guy to simulate the power system experiments. And for torque value you can apply. You can apply via the constant data. Take a constant. And we are going to apply 1 Newton meter, and here just open the bus selector. Here all the measurable signals will be available. Just choose whatever the signals do you want, and I choose all the signals and take scope. Here the 4 signals are there. We have to change the scope settings for 4 signals. And change the color settings also. If you need, you can change it, else just leave it. And signal 1 and signal 2, similarly you have to apply all the things. Here itself we can apply. And signal 3 for signal 3 also, and similarly signal 4. So now we have applied all the signals, the scope setting. To connect this scope to the signal just save the simulation. Before running the simulation, please save the file, then only simulation will work. Now we can run the simulation for one second, and let us check whether the machine is started or not. And whether we are getting all the signals or not. See, the simulation is running. Before the simulation, we have to verify the voltage levels, whether we have applied the corresponding voltage. For armature, we should apply 240 voltage, and similarly for the field we have to apply 300 voltage. So yeah, see here the machine has started from 0 to about 240 radian per second. It's a radian per second. Generally, in the MATLAB environment, the speed will be measured in the radian per second. If you want to convert to RPM, just add it 30 by pi in the signal block. So by adding the gain function to that block, just multiply with the 30 by pi. Then you will get the speed in RPM unit. So now the perfectly machine is running. So now we have to apply the controller to this machine. So earlier as per our block diagram, we have to develop a control circuit for this machine. So for the control circuit generally will be for DC motor, H bridge, for H bridge power converter. So for H bridge power converter, we have to take a MOSFET. So just to connect the MOSFET as a H bridge configuration, and by applying the PWM to this MOSFET, again we can control the speed. But in this simulation, we are going to design the controller for all the modes called forward motoring, for reverse motoring, similarly forward braking and reverse braking. So we are going to introduce a braking system also to this motor. So then we can say this as a 4-quadrant control. For generating a PWM, we need a repeating sequence. So the repeating sequence, you can the time value is nothing but a x-axis. For x-axis, just apply the value like this, and the switching frequency you can keep 1 kilohertz maximum. And y-axis, this is the y-axis value. So just keep like this. And we need a control logic. So now we have to take a logic operator and a relational operator. So by adding the relational operator, we can compare the voltage, take a constant block to compare the value. So now the idea is, so whenever the threshold value called the constant value goes above 0.5%, then motor will be in the one direction called the forward direction or reverse direction. Similarly, if below that value, then the motor we can decide as a again forward motor or reverse motoring. For example, if we by changing this logic, we can check whatever it is actually. So we will verify the logic in the simulation output. So I will explain you detailing in the simulation output. And so now the PWM is ready. So again we this PWM is for 2 MOSFETs. Similarly, we have to generate another MOSFETs. For that we need logic operator. Take a NOT gate. The this PWM pulse for 1 and 4. So let us take this is PWM MOSFET 1, 2, 3 and 4. So similarly, we have to apply the reverse pulse for PWM 3 and PWM 4. Yeah, so from this we have to connect the motor in between the 2 legs. Right? Just save the simulation. So now if you run the machine, so it will be a negligible speed because the carrier waveform equally divided into 2. So now almost it will be negligible speed. Yeah, see, all of very zero speed, but we have to change it actually. If you change the speed 0.9, so let us take 0.9, then the motor will be in the one direction. Yeah, see here the motor has rotated in the forward direction. Similarly, if you reduce it less than 0.5, if you, for example, if you take a 0.2, then it will be in the reverse direction. So during that period, this 1 and 4 will be in the lesser PWM, and then 3 and 4 will be the high pulse width. See here the motor is rotated in the negative direction. So now we have to generate an automatic logic here. We have to apply the brake. So for that we are going to take one additional block called the switch block. Take a switch block. So this, by using this switch block, we can implement the logic. So for the motoring applications, take again the constant block. Suppose if this constant block is 1, then we can assume that the system is going to work in the motoring up period. So let us take, this is a reference signal. The idea is, if this signal is above 0, then this signal will be passed out. Otherwise, this signal will be passed out. So now, for motoring applications, you have to directly apply to the PWM, to this MOSFETs. For braking applications, you have to turn off the topper switches and then you have to enable the bottom switches. So both, if you enable both the bottom switches, then the inside the motor available in the back EMF will be dissipated within the motor itself. So in that conditions, the speed of the machine will drastically reduce and then it will approaches 0. So that is the idea for the braking. So now, for the MOSFET 1, yeah. See, for example, if you take a PWM for 1, first switch, yeah, just remove the PWM from the existing, take a go-to block, so take, this is a S1, and just select and drag the second from block, so you will get the from block. Otherwise you have to search it and from the library, and then you have to connect accordingly. Yeah, so now the S1 has connected, and see, if this is for motoring, so this condition is valid. So this signal will be directly passed to this S1 block, then directly it goes to S1. And similarly, if it is a braking application, so what we have to do? So we have to disable the function. Then we have to enable the this switches, and we have to disable this switch. So we will program it later. Right? Take a few more switches also. Yeah, this is for S2, and this is for S3, and this is for S4. Right? So for S1, S2 PWM is this one, and similarly S3, this is for S4, S3 also the PWM like this. So now the common threshold logic is, you have to take a common logic. The logic function is common for all the switches. So now we have to enable, turn on the S3 and S4. So for that we have to apply 1. Just take again the constant block. We have to apply S3 and S4 1. And for here we have to apply 0. That is, we have to open the PWM. So for that, just take a NOT gate. Yeah. So now it is perfect. For this block, if it is a 1, then it will be a motoring function. So for the motoring function, that the switch will work, will function to pass the PWM block to here. So from here, the PWM will be applied to the MOSFETs. Suppose if the motoring, if this switch is disabled or converted to 0, that is for the braking mode, then similarly this PWM will be disabled and this PWM will be applied. Just S4, this is S4 block. This is S4 and this is S2. And this is S3. Then we can run the simulation. See, now the system is in motoring operation. Motoring operation. The motor brake is not enabled. See, that is in reverse mode. If you want to change in the forward mode, just apply here. Run the machine for infinite time, so that we can run, we can change the data and verify the simulation. Run the simulation. See here, the motor is working in the forward direction. So now I am going to apply the brake. So if you apply the brake, the motor will be stopped. And again motor, I am going to release the brake and I am going to run the machine in the reverse direction. That is the reverse motoring. And after some time we will we can run for reverse braking also. Just to operate here braking. Now I have applied the brake. So just to stop the simulation. Enlarge it. See here, this is the forward motoring. I have applied the brake, so the brake has been applied, and after some time again I have converted to the forward motoring and then reverse motoring. Finally, I have applied for the brake, reverse brake. So like that, we can implement the control logics to the DC motor control. Okay, so now we have to go for the closed loop option. So this is just an open loop option. So now we can go for the closed loop option. So in this closed loop option, so the same logic, in addition to that, PI controller has been implemented. So for that one, first PI controller, we are going to take a speed. So speed as a radian per second parameter, and that actual speed measured with the reference speed. So in this reference speed, we have the basic PI logic has been implemented. So you can download the simulation in the from the LMS portal. You can start using this simulation. And similarly, the same idea has been implemented in this simulation. And for the speed for initial speed control, for actual speed of the motor has been taken into that account. From this block we can get a reference current. So from this reference current, so we have to measure, we have to compare with the actual current. For that we are going to take a motor current also. So in this block, just we are going to compare. These two are the just filters, just to use it, and compare with the actual and reference. So from this again we are going to use the just basic controller, PI controller. So from here we are going to compare with the reference voltage along with the carrier signal. So this carrier signal is again the repeating sequence 1 kHz frequency, switching frequency. If you apply the motoring operations, then the pulses has been generated based on the system. So now we can run the simulation. See, now it is in the negative speed. Just to change the reference speed, so it is in the omega radian per second. So convert to the positive speed. Earlier it was the negative speed, now it is the positive speed. Yeah, so from negative speed to positive speed has been converted. And for here you can apply the brake. If you apply the brake, yeah, so the brake has been applied. Similarly, we can go for the just before changing the speed, you have to release the brake, enable the motor, yeah, now forward mode, and change for the reverse speed. Yeah, so the reverse speed will be enabled. So like this we can change the motor speed directions and all. So this is again a complete speed control of induction machine. So here, sorry, speed control of DC machine. So you can use this as for your research purpose. So you can start your research from this point of onwards. This is eligible to submit your final year projects also. For more modification here, we can also implement a fuzzy logic or some of AI logic also we can apply here. So that is additional custom requirements. So for your custom requirements, you please contact our people. We will give you, you will get more support on this. So here in this demonstration we have verified forward motoring and then reverse motoring, similarly forward brake and reverse brake. So here this DC motor is mainly used for this kind of applications. These are some basic theories, so you can check it. Generally for the DC motor applications in the commercial market, for all kind of conveyors these kind of machines are used. So that here the conveyor can handle speed as well as that weight. Similarly, the kitchen equipments and then packaging equipments and some of the machining milling and lathe equipments. These are all some high-end machines. So similarly, again dedicated equipment applications called electric locomotive and then hoist applications and all. So people are using this kind of DC motors. But actually in the particular topic or particular applications, we can construct our own machine with a variety of new advancements available in the motor technology. Called actually the PM DC machine is the very basic motors. In this DC machine, so we can get a BLDC and SRM and flux machines. These are all additional special machines in this category. So based on your requirement, we can choose the things. And finally, in our series, we have scheduled a DC motor, induction motor, BLDC, and PMSM. So 4 motor is in our in our schedule. So after finishing the schedule, so we will discuss how to choose the motor for our applications. So that we will discuss in detail later. And thank you for your valuable time. So if you have any queries, you please comment it. We will give you the answer and as soon as possible. And but you please keep engaged with the entire session, so you will get definitely you will get rich knowledge in this power electronics segment using the MATLAB. So thank you once again for your valuable time.